Okay, grade 11, welcome back. We're finished with all of the work we're going to do now on chapters 5 and 10, linear models and financial applications. We're going to move on now. And we need to go back, and I know you've been voting for two different learning pathways, and I'm happy to let you guys decide. Simple majority will rule. And I suppose I'll break the tie if I have to. Let's hope it doesn't come to that. We got to go back and tidy up a couple little ideas in chapter 1 because they're kind of foundational ideas that we're going to need at various points throughout the course. So I thought while we're still deciding as a group what we're going to do next, whether it's chapters 2 and 3 or as a package, chapters 4 and 6, we're going to go back and do some of this fundamental number work or numeration work to make sure that we're ready for all the challenges that lie ahead in this regard. So we're not doing all of it, and the reason we're not doing all of it is because some of the topics that are going to come up in this chapter, we can sort of learn through inference and implication through other parts. We don't need to specifically address them. We can address them as the need pops up later on when we're studying other parts of the textbook. Okay, but those ones I've highlighted in yellow there, they are the ones that we're going to be doing here. Now, let me just read this. When we take measurements, we're usually reading some sort of scale. When we measure something about an object, perhaps its weight or its height or color or all sorts of things, pressure, barometric pressure, is likely to fall between two divisions. And those divisions are the scales or the little graduations, those little notches on the side of your measuring device. We approximate the measurement by recording the value at the nearest graduation mark or nearest scale mark. But in doing so, our answer may be inaccurate by up to half a unit. Well, what does that mean exactly? If I were to measure something and I'm going to report its precision, I had to have made a rounding off decision. I decide to report the nearest number that I can based on the markings on the side of the measuring device. So I've put a little dial type scale, like something you may have on an old-fashioned bathroom scale, or perhaps a hygrometer where you're measuring pressure, or I don't know, a number of different things that have a kind of a round scale. If something's pointing at 1, indicating maybe, something weighs 1 kilo in the grocery store, and then later on you add more to it, it becomes 2 kilos, and that's the way you read it. At what point would someone say, all right, I'm no longer calling this 1, because there's a lot of spaces in between the 1 and the 2. The question becomes then, at what place in between the two do you stop calling it 1 as the nearest one, and you start calling it 2 as the nearest one? And that's why this textbook says a measurement is accurate to either plus or minus. That's what that funny little symbol means in front of the 1/2 here. It's either plus a half or minus a half of the smallest division on the scale. So in this particular case, if we measure something with this scale, it indicates that the size is 2, then in reality, it would have captured everything that's bigger at 1.5 or bigger, because nothing smaller than 1.5 would be reported as 2. It would be reported as 1, all the way up to, but not including 2.5. And I say not including 2.5 because of this. Remember, when you reach 1.5 or the middle, when rounding off, it goes up. And anything just short of the middle continues to stay down. In this second case, if I have included less than or equal to, the equal part would have gone up to the next one, which in this case would have been 3. So we had to watch the types of inequality signs we're going to use. Okay, Ling uses a ruler to measure the length of her pencil case. She records the length as 18.7 centimeters. Okay, now already I'm looking at that precision. The nearest choice that she had was 0.7. So what does that actually tell you? It tells me that she didn't choose 0.6 and she didn't choose 0.8. That means the length of her pencil case was nearest to 18.7, but not necessarily precisely 18.7. So how do we do that? I've taken a look at her pencil case. Here it is. And I put a ruler underneath it so we could measure it accurately. Now, I'm not sure how good your eyesight is, but mine's not good enough to read that. So what I'm going to do is I'm going to blow it up. No, it's not really much good, is it? But we're going to have to deal with the formula. The formula says this. If she is able to the nearest precise marking on that ruler, come up with 18.7. Here's a good way of doing it. I'll make my own ruler and show you where 18.7 is. If we get nearer, if we blow that up near this red area here, that indicates 18.7. There's 18, there's 19, this is 18.7 here. I'm going to blow that up there. And you can see that kind of like the catchment area for 18.7 is the small vicinity around 18.7. So that would mean between 18, well, it's halfway between 18.6, which is over here, and 18.8, which is over here. So what do we call that number here that's halfway between 18.6 and 18.7? That's the one that's here. And that's what the previous slide was telling us. It's plus or minus a half of whatever the most precise marking on your measuring device is. So if I was to take half of 0.7, that would, or half of a unit, it would be half less and half more. And that would be 18.65 and 18.75. And that's sort of like the little catchment area or the vicinity, the neighborhood that belongs to 18.7. And we're going to have to get used to doing this ourselves. So each of these slides, I would like you to pause and try and answer them. You'll see the answers upside down at the bottom, so it doesn't, a dead giveaway. And you can work these out in your exercise book. So each new question, hit pause. The ones that are highlighted in blue, I'm going to come back and solve with you. Okay, so hit pause, and then when you've done these four, you can hit resume. Okay, I'm assuming you're on the next question. Now, when you get here, hit pause, and when you've done this one, you can resume. Okay, here's a couple more we're going to try. Answers are upside down at the bottom. When you get to this slide, hit pause and try the questions at the bottom. Okay, one more. Here we're going to be using a digital thermometer to the nearest tenth. You can go ahead and try this question, hit pause, and then hit resume when you're ready to begin. Now here's one highlighted in blue, and I'm going to solve this one for you. It says a rectangular block of wood measured 78 centimeters by 24 centimeters. So what are the boundary values for its perimeter? Well, this is an interesting little question. What I'm going to do is I'm going to draw, remember anything visual, you want to have a picture of it. I'm going to try and draw a rectangle here whose length is 78 and whose width is 24, but we're asked something about the perimeter. Well, what I need to do is come up, this is the length and this is the width. I want to come up with the boundary values, the accuracy of the boundaries for each of those variables. Now the length would be bigger than up to a half less, so it would be 77 and a half all the way up to 78 and a half, because that is a half more and a half less than the reported length. If I was dealing with the width, I would say that it is 23 and a half at its smallest and 24 and a half at its biggest, because that's plus a half and minus a half of the most accurate that we have in those measurements. So now we want to know what are the boundary values for its perimeter. Well, let's remind ourselves the perimeter is twice the length and twice the width. And what I do is if I want to find the boundaries of the perimeter, I take the smallest length and smallest width and I place them in both of these positions, and that will give me the smallest perimeter. If I want to find the biggest possible, it would have happened when the biggest possible length was used and the biggest possible width was used, and I would do the same there. So I've just computed 77 and a half twice, oopsie, twice, 23 and a half twice, added them together, and the smallest the perimeter could actually be is 206. Whereas if the length was the biggest it possibly could be and the width was the biggest it could possibly be, the biggest the perimeter could possibly be is 2 of these and 2 of these, and that would add up to 206. Oh, sorry, this one was 202. I made a mistake. That's 202, and this one was 206. All right, let's move on. Here's another set of questions. I'd like you to try them. Hit pause, and when you're ready to resume, you can hit resume. Here's another question for you to try. Hit pause, give it a try, and hit resume when you've done. Okay, we're back to another blue one here, and I'm going to solve this one for you. Here we're going to be talking about the area, and it said that we've got a paver stone. That's one of those like patio slab kind of concrete tiles. Well, it wasn't very well drawn, but it said it was near enough to 18 and 10. So what I need to do is, like before, I need to consider what's the biggest and smallest that the length could have been, and what's the biggest and smallest that the width could have been. Well, again, this is to the nearest unit, so I'll go half minus and half plus, meaning it could have been as small as 17 and a half, any smaller than 17 and a half, and we would have called it 17 straight out. And all the way up to, but not including, 18 and a half. Any bigger than 18 and a half, and we would have called it 19. Same is true with different numbers here. The smallest the width could have been was that, and the biggest would have been that. So what are the boundary values for the actual area? Well, we need to recall that the area, oops, that's width, that's length, and the area is the product of its length and its width. So that's exactly what I'm going to do. So what do we have here? Whoopsie. We have that the smallest possible width, that's right, area is 166.25 or a quarter, and the biggest possible one is the product of these ones over here, and that's going to give me 194 and a quarter or 0.25. You can see that's quite a generous difference between the two, and that's exactly where this conversation is going to lead us, is to, the importance of precise measurements and what kind of inaccuracies can be suffered if we're not really aware of it. Okay, here's a series of questions for you to do. 1, 2, 3, 4, 5, 6, and 7. I'd like you to try those 7 questions. Please ask for my help. I'm here to help you, and I want to help you and get this all correct. And it's going to get, it's starting out quite mildly, but it's going to get quite more demanding as we get nearer to the end. Hit pause now and try these 7 questions. The answers are on the next slide, so you can go back and forth between that slide and the answers on the subsequent slide. I'm going to go back here. Please hit pause, and when you're done with this, we'll continue together. Okay, I'm assuming that you've finished this panel of questions now, and you've been consulting with the answers on the next slide, and that's it. So we've done our first section, and now we're ready to move on. This is section 1C of our textbook. Several questions here, doing the same kind of thing. We're not doing all of them as usual. We've got the guidebook here. This is section 1C, as you can see here, no pun intended, and we've got that part right in there to do, and I'm here to help you. We'll get the textbooks out, and we'll get this done in no time. Okay, well done.